For the first time, scientists have discovered animals living underneath the ocean floor. Last summer, researchers from the Schmidt Ocean Institute set out to explore marine life around hydrothermal vents. Now, they've published their findings. Hydrothermal vents shoot water from cracks in the seafloor.
At 5,000 meters below the Pacific, in crushing darkness, scientists found something impossible: oxygen forming without sunlight or life. The seafloor wasn't dead. It was moving, breathing, and possibly thinking. What started as a mining mission turned into a discovery that might redefine life itself, on Earth and beyond. Descent into the abyss. In 2021, a team of scientists led by Dr. Andrew Sweetman from the Scottish Association for Marine Science descended into one of the least understood regions of Earth, the Clarion-Clipperton Zone, CCZ. This remote abyssal plain lies between Hawaii and Mexico, spanning over 4.5 million square kilometers, larger than the entire European Union. At a depth of 5,000 meters, it is a place of extremes: no sunlight, near freezing temperatures, and pressures over 500 times higher than at sea level. It is the closest thing Earth has to an alien world. Most expeditions to the CCZ are driven by economics. The ocean floor here is littered with polymetallic nodules, dark potato-sized rocks loaded with manganese, nickel, copper, and cobalt. These metals are critical for building batteries, electric vehicles, and renewable energy systems, with an estimated total value in the trillions. But Sweetman's team wasn't after treasure. They came for something even more essential: oxygen. Their goal was to study how oxygen moves through deep-sea mud, an important clue in understanding how life survives in such extreme environments. Using robotic landers equipped with benthic chambers and oxygen sensors, they aimed to measure how microbes consume oxygen in this silent, dark world. But what they discovered defied everything we thought we knew. Instead of seeing oxygen levels decrease, the instruments showed them rising. It was as if something in the sediment was creating oxygen out of nothing. You learn to distrust your instruments when you're 5 kilometers below the ocean, one of the researchers said. But even after repeating the tests multiple times, adjusting the sensors, and deploying fresh equipment, the anomaly remained. The oxygen kept rising. This wasn't just unexpected, it was impossible. And just when they thought they might have stumbled onto a glitch, the next phase of the investigation would take them deeper into the unknown. What if microbes weren't responsible at all? The setting: a world beyond surface life. At a depth of 5,000 meters, the ocean becomes something else entirely. This is not a place humans were ever meant to explore. It's cold, just a few degrees above freezing. It's completely dark. Sunlight doesn't penetrate even half that depth, and the pressure is crushing, 500 times greater than what we feel at the surface. Yet here, on the floor of the Clarion-Clipperton Zone, life has found a way. To the naked eye, the seabed appears barren: endless mud, rocks, and the occasional drifting creature. But lying across this desolate floor are countless polymetallic nodules. They look like lumps of coal or old potatoes, but they're filled with high-demand metals like nickel, cobalt, manganese, and copper. That's why mining corporations have had their eyes on this area for decades. The nodules are seen as the future of clean energy, essential for building the batteries that power electric vehicles and renewables. But underneath that economic ambition lies a scientific mystery. This landscape, long considered a dead desert, is more active than anyone suspected. When Sweetman's team deployed their robotic instruments, they didn't just find strange oxygen readings, they began to see signs that the environment itself was behaving in ways we don't understand. This wasn't just geology. Something alive, or something acting like it, was happening on the ocean floor. And as we'll see next, the anomaly with oxygen wasn't an isolated glitch. It was the start of a pattern that would challenge the very fundamentals of Earth science. The unexpected oxygen signal. When scientists placed their robotic landers on the seafloor, the mission seemed straightforward. Inside each lander was a benthic chamber, essentially a sealed dome that holds a mix of deep-sea mud and surrounding seawater. Attached to these were sensitive oxygen sensors, designed to monitor how much oxygen remains in the water over time. In theory, oxygen levels should decrease as microorganisms in the mud consume it for energy. This is how most sediment ecosystems function, even in the deep ocean. But within hours of data collection, the results took an alarming turn. Instead of declining, oxygen levels were rising inside the sealed chambers, an observation that violated everything scientists understood about biological respiration. At 5,000 meters depth, where no light penetrates and temperatures hover just above freezing, oxygen isn't supposed to form. There are no plants, no photosynthesis, and yet, the sensors showed increasing concentrations. At first, the team suspected the instruments were malfunctioning. "You learn to distrust your instruments when working at these depths," one crew member said. "Salt water can corrode even the best equipment. Deep ocean pressure can distort metal, and the cold can interfere with electronics." The team recalibrated the sensors, cleaned the chambers, and even launched additional landers to new sites across the Clarion-Clipperton zone. But the results remained the same. Oxygen kept appearing. This wasn't a single anomaly, it was repeating, consistent, and measurable. The only known processes that produce oxygen, like photosynthesis or industrial electrolysis, require light or powerful external energy sources. None of those were present here. And yet, oxygen was being produced slowly but unmistakably in total darkness, 5 kilometers beneath the surface. At that point, the scientists had to consider something radical. Was there a chemical process happening on the ocean floor that we had never seen before? Could minerals in the mud be reacting with salt water to create breathable air? Or was there some form of unknown life performing a kind of photosynthesis without light? Whatever the answer, the rules had changed. For the first time, scientists were watching Earth's chemistry behave in a way it never had before in recorded history. This wasn't just a breakthrough. It was a signal that something in the deep ocean had escaped our understanding. But before diving into wild theories, Sweetman's team did the only thing responsible scientists could do. They tried to eliminate the most obvious culprit, life itself. And what they discovered next would only deepen the mystery. Eliminating life, the mystery deepens. If microbes weren't the cause of the rising oxygen, the team needed to prove it. They designed a new round of experiments using biocides, chemical agents capable of killing all living organisms inside the benthic chambers. The goal was simple: sterilize the environment. If oxygen still appeared in a lifeless system, then the cause had to be non-biological. Once again, robotic landers carried the chambers, now fully sterilized, down to 5,000 meters. Conditions were tightly controlled. There were no organisms left to consume or produce gases. According to known science, the oxygen levels should have remained flat or declined slightly, but that's not what happened. Just as before, oxygen levels increased, slowly but undeniably. This eliminated microorganisms as the source. No bacteria, no archaea, nothing living. Yet, the pattern repeated. Air was forming where it shouldn't. At that point, one researcher noted, we had to admit this wasn't just strange data. This was a real, repeatable event. We were watching the rules break themselves. Even more puzzling, the results held across different chambers, locations, and pressure conditions. Whether the chambers were deployed 10 kilometers apart or with different sterilization doses, the outcome was the same. Oxygen rose inside lifeless sediment. Chemical and geological theories came next. Was there seawater-mineral interaction producing gases? Could metal ions in the sediment somehow generate oxygen through a slow, unknown electrochemical process? The data was limited, but the phenomenon was stable and consistent. It was as if the seabed was breathing, not with lungs, but with mechanisms we didn't yet understand. Other research teams joined the puzzle. Experts in geochemistry, marine physics, and deep-sea biology began weighing in. No one had a solid answer. And that's when Sweetman's team started considering the strange electrical signals they'd been picking up. Low-level currents, barely measurable, but present. The pieces were starting to align, but the picture they painted was something entirely unfamiliar. A world where air forms without life, where voltage pulses through the rocks, where the line between geology and biology begins to blur. And it was all tied to one strange object, a rock that didn't just sit in the mud. It might be doing something. Next, they'd find out just how active these polymetallic nodules really were. A battery in a rock, the polymetallic clue. The seabed of the Clarion-Clipperton zone, CCZ, is scattered with what look like lifeless lumps of charcoal or stones. Known as polymetallic nodules, these potato-sized rocks have long been targeted by mining corporations for their rich deposits of manganese, nickel, cobalt, and copper, key metals used in electric vehicle batteries and renewable technologies. But something Sweetman's team noticed during a 2022 deep-sea conference changed everything. A passing comment described these nodules as batteries in a rock. It was meant as a metaphor. But for Sweetman, it triggered a possibility that was far from metaphorical. Back on the research vessel, the team began testing the nodules not for their market value, but for electrical activity. Using precision instruments, they measured the surfaces of several nodules taken directly from the seafloor. What they found was subtle but undeniable. A steady electrical potential, just under 1 volt, was consistently present. It wasn't much, less than a standard AA battery, but in the right conditions, even that small voltage could initiate electrochemical reactions. That's when a hypothesis began to form. What if, under extreme pressure and saltwater exposure, these nodules weren't just passive rocks? What if they were generating electricity naturally and using that energy to split seawater molecules? This process, known as electrolysis, is the same principle used in labs and factories to produce oxygen and hydrogen from water. But in this case, the nodules seem to be doing it on their own, at 5,000 meters depth, with no input from human technology. This theory offered the first real explanation for the rising oxygen levels observed in sterilized chambers. The metal content of the nodules, combined with salt ions in seawater and intense deep-sea pressure, could be triggering a natural electrochemical cycle. In effect, these rocks might be creating dark oxygen, air produced without light, without photosynthesis, and without life. The implications were staggering. These nodules weren't just mineral deposits, they were functional elements of a hidden deep ocean system, slowly exhaling oxygen into a world we believed was inert. What's more, they might have been doing this for millions of years, undetected beneath the waves. As Sweetman put it, we weren't looking at geology anymore. We were looking at something that acts like it's alive. And as the team dug deeper, the rocks would reveal another secret, one hidden not in their chemistry, but in the very shape of the seafloor they rested on. Visual and geophysical anomalies. It began with photos. For weeks, the team's landers had captured images of the Clarion-Clipperton Zone seafloor, but when lined up, the images showed something impossible. The ground was changing. Ridges rose, spirals formed, grids aligned with eerie precision. This wasn't random sediment shifting, it looked deliberate. At first, they suspected faulty cameras, but then came electromagnetic scans, and each pattern change matched tiny magnetic pulses. Every ridge, curl, or line was synchronized with bursts of unseen energy. It's like watching the Earth think in slow motion, one scientist said. The shapes didn't match erosion, tectonics, or marine life. They didn't behave like geological structures. They looked self-organized, as if the seafloor was responding to an unknown force. Historic maps confirmed the patterns weren't new, only more complex now. And since observation began, changes were accelerating. The patterns seemed to know they were being watched. One researcher whispered, "We're not just observing, we're part of it now." Whatever this was, it wasn't lifeless. It wasn't static. The seafloor was alive with structure, evolving under pressure, cold, and silence. And it posed a deeper question. If the ground itself is changing and producing oxygen, what else could exist, hidden in the dark? The origins and implications for life. For decades, we believed oxygen, the fuel for most life, could only come from photosynthesis, powered by light. But findings from Dr. Sweetman's team in the Clarion-Clipperton Zone challenged that idea. At 5,000 meters below the surface, in total darkness, they recorded rising oxygen levels in sterile chambers, without plants, algae, or light. The cause? Natural electrochemical reactions from polymetallic nodules. These metal-rich rocks generate faint voltages, under 1 volt, when exposed to deep-sea pressure and salt water. That's enough to split water molecules, releasing oxygen and hydrogen, mimicking electrolysis, but occurring naturally. Scientists now call this process dark oxygen production. This rewrites our view of what conditions are required for life. If oxygen can form geochemically, life could exist without sunlight, on Europa, Enceladus, or Mars, where similar conditions may exist. It also reframes how early Earth might have supported life before photosynthesis began. Sweetman's team is now collaborating globally to model these deep-sea oxygen systems. We assumed sunlight was life's spark, one scientist noted, but maybe the Earth itself breathes. Yet, the same nodules producing this oxygen are targeted for mining. In chasing minerals, we may be disrupting the planet's oldest, and possibly universal, oxygen engine. The mining dilemma, risking the unknown. The Clarion-Clipperton Zone, CCZ, is now at the center of a growing conflict between resource extraction and scientific caution. The polymetallic nodules, once seen as inert rocks, are now suspected to play an active role in producing oxygen deep beneath the sea. Yet these same nodules are rich in nickel, cobalt, and manganese, key materials for electric vehicle batteries and green technologies. Mining companies, backed by nations and licensed by the International Seabed Authority, are preparing to harvest them on an industrial scale. But findings from Sweetman's team suggest these rocks might be more than mineral deposits. They could be part of a delicate electrochemical system. Disturbing them risks unknown consequences. Over 25 countries and several environmental organizations are calling for a moratorium on mining. Early simulations show sediment plumes, oxygen disruption, and microbial loss. The nodules grow slowly, just millimeters per million years, and once gone, they can't be replaced. We still don't know how widespread the phenomenon is. If global deep-sea mining could alter Earth's oxygen systems permanently, as one scientist warned, we're dismantling a system we haven't even begun to understand. Do we mine the unknown or pause before undoing something ancient and vital? The scientific debate and unanswered questions. As data from the Clarion-Clipperton Zone spread, it sparked intense scientific debate. Could oxygen really form without light or life? It challenged long-held beliefs in biology and chemistry. Skeptics suggested undetected microbes or sensor glitches despite sterilization and repeated trials. But the results were consistent. Oxygen levels rising in sealed, lifeless environments across multiple locations. Readings from the polymetallic nodules confirmed weak electric currents. The geometric shifts in the seafloor and related magnetic pulses couldn't be explained by erosion or known life forms. Still, the underlying mechanism remains unknown. Scientists don't know how widespread this phenomenon is, or if it could support ecosystems. Terms like abiotic oxygenation are being discussed cautiously. If true, it may reshape our understanding of how Earth, and possibly other worlds, support life. It's not just about the ocean anymore, said one planetary scientist. It's about redefining what makes an environment habitable. But time may be running out. Mining efforts are moving forward, and we might lose this unknown system before we even understand it. What comes next? A new frontier. What started as a mission to study oxygen in mud has turned into a global mystery. Sweetman's team is planning new expeditions. Other scientists are joining, deploying advanced landers, electromagnetic sensors, and biochemical tools, not just in the CCZ, but across Earth's deep oceans. This is no longer just environmental science, it's planetary systems science. The International Seabed Authority is facing pressure to pause mining until more is understood. Scientists warn the polymetallic nodules, now seen as deep-sea batteries, may be part of an ancient and vital oxygen cycle. Humanity stands at a crossroads. Treat the deep ocean as a resource or as critical life infrastructure. We've long believed the deep sea was silent and inert, but now it seems alive, with processes we barely understand. We thought we were observing, one researcher said, but we may already be part of the system. What if the first sign of universal life logic didn't come from space, but from 5,000 meters beneath the sea?
And what if it's watching us back?
We searched the ocean's floor for minerals and found something alien. This discovery may change how we see our entire planet.